Hello and welcome to the Space Above Us. Episode 90, Space Shuttle Flight 23, STS-61B. Ease of Access. Last time, we talked about the flight of STS-61A, also called D1. Spacelab flew again with a record-breaking 8-person crew, and West Germany picked up the tab, making this the first shuttle payload operated from outside the United States. I also stumbled my way through some butchered German pronunciation and discovered that I actually do have some German listeners. I bet you all can't wait until the D2 mission a little bit down the road. Before we get started with today's mission, I have a quick detour in the form of a fun fact. The week before Atlantis lifted off on STS-61B, another space shuttle lifted off on its own voyage. Last featured back on episode 66, the approach and landing tests, Enterprise was taking to the skies once again. OV-101, NASA's first orbiter, was instrumental in sussing out the flight characteristics of the space shuttle as it prepared to touch down after re-entry. It was originally intended to be retrofitted for spaceflight, but the design had changed enough that it just wasn't cost feasible to do so. Instead, after its 5 free flights over the deserts of Edwards Air Force Base, Enterprise was used for fit checks and publicity displays. Incidentally, since Discovery never launched out of Vandenberg on STS-62A, Enterprise is the only orbiter to be erected on the West Coast Shuttle launch pad. When it was clear that NASA had done all that it could with Enterprise, arrangements were made to transfer the vehicle to the Smithsonian Institution. On November 18, 1985, Enterprise, atop the shuttle carrier aircraft, flew from the Kennedy Space Center to Dulles International Airport just outside Washington, D.C. Once there, the Smithsonian took ownership of the would-be spaceship, preparing it for public display. But that display wouldn't come anytime soon, with Enterprise remaining in a hangar until 2003, when it was finally able to be viewed by the public in the Udvar Hazy Center, an extension of the Smithsonian's Air and Space Museum. So with that, we thank Enterprise for its service and say farewell. Well, for now at least. We haven't quite yet seen the last of Enterprise. As NASA was saying farewell to Enterprise, it was also looking forward to the next decade in American spaceflight. With the space shuttle finally flying regularly and proving itself to be a reliable workhorse spacecraft, it was time to put it to use on more than just ComSat deployments. What do you do with a fleet of spacecraft capable of carrying voluminous and massive payloads into low Earth orbit on a regular basis? You build a space station, of course. I briefly mentioned it before, but firmly on NASA's radar was the proposed Space Station Freedom. We're not really going to get into it here since I think it'd be more appropriate to cover when we get to the International Space Station flights, but let's hit the main points. Space Station Freedom was announced in the mid-1980s and was intended to provide NASA with a permanent human presence in space. The station would be multifaceted. Like Skylab, it would be an important source of science, collecting data that would be impossible on the ground. With all of the commercial pharmaceutical experiments already flying on space shuttles, it would likely be a place for microgravity processing. And with an eye towards complex science spacecraft on the horizon, such as what would eventually be known as the Hubble Space Telescope, it could be a facility for on-orbit servicing and repair of satellites. In fact, one of the objectives on this mission was to test flight control software that could be used on the proposed Orbital Maneuvering Vehicle, a space tug that could retrieve and deploy spacecraft from the space station. Unlike Skylab, which was launched all in one go, minus a solar array, Space Station Freedom would be assembled on orbit. This meant that NASA had to learn how to, assemble things on orbit. And perhaps learning their lesson from the difficulties associated with extravehicular activity in the mid-1960s, they were easing into this new challenge. There were questions like, could astronauts assemble a large modular structure in space? Once they assembled it, could they move it? Could they disassemble it? Is it possible to keep the crew near the main station, building new structures by adding onto the quote-unquote bottom, sort of growing it out into space? Or was it better for crew members to crawl around on the structures itself as they built them? Did in-space assembly closely match the experience of simulations in the neutral buoyancy pool? And perhaps most importantly, what unanticipated difficulties would be encountered when they tried this out for real? With all of that in mind, STS-61B would feature 2 EVAs that would each focus on answering all of these questions by assembling and disassembling structures in Atlantis' payload bay. We'll get into exactly what and exactly how in a little bit. But first, let's meet our intrepid crew. Or our Atlantis crew. Funny joke. Commanding the flight was Brewster Shaw, who we last saw as pilot on STS-9. This is his second of 3 flights. Joining Shaw up front was pilot Brian O'Connor. Brian O'Connor was born on September 6, 1946 in Orange, California. O'Connor has a textbook pilot-astronaut career. U.S. Naval Academy, Masters in Aeronautical Systems, flew a bunch of different aircraft including the Harrier, became a test pilot, flew really weird stuff like the X-22, and then became an astronaut in 1980. This is his first of 2 flights. Mission Specialist 1 is someone who we're going to be seeing a lot. Jerry Ross. Jerry Ross was born on January 20th, 1948 in Crown Point, Indiana. He stayed in Indiana, attending Purdue University, where he earned a bachelor's and master's in mechanical engineering. From there, he joined the Air Force thanks to his ROTC involvement in school, heading to Wright-Patterson Air Force Base to work on ramjets. He spent the next few years in a variety of roles, including Chief Flight Test Engineer for the B-1 bomber. He joined NASA by way of the Payload Operations Center at Johnson Space Center in 1979, before being selected as an astronaut in 1980. Specializing in EVA, he'll be one of 2 people leaving the crew cabin on this mission. I said we'll be seeing a lot of him because he was the first astronaut to fly on a remarkable 7 missions, breaking the record set by John Young. Joining Ross at the back of the flight deck was Mission Specialist 2, Mary Cleave. Mary Cleave was born on February 5, 1947 in Southampton, New York. As you might expect from a mission specialist, she has an almost alarming amount of education, with a bachelor's in biological science from Colorado State, and a master's in microbial ecology and doctorate in civil and environmental engineering from Utah State. Her research went into some pretty cool stuff that looked at how environmental changes affected local ecosystems, but we won't get too into it since in 1980, only a year after receiving her doctorate, she was selected as an astronaut. This is her first of 2 flights. Joining Jerry Ross on a walk outside the orbiter would be Woody Spring. Sherwood Spring, who went by his nickname Woody, was born on September 3, 1944 in Hartford, Connecticut. Spring earned a degree in general engineering from West Point and later a master's in aerospace engineering from the University of Arizona. He did 2 tours of duty in Vietnam, flying helicopters during the second tour. When he came back, he learned to fly airplanes, eventually working his way through the Navy's test pilot school and ending up at the Army's flight test facility at Edwards. He was selected as an astronaut in 1980, and this is his only flight. The flight also had 2 payload specialists. Payload Specialist 1 was Charlie Walker, who we've seen fly twice before on STS-41D and STS-51D. And since he's here, that means, that's right, CFIS, the Continuous Flow Electrophoresis System, will also be flying, taking advantage of the microgravity environment to process tricky pharmaceutical products. This is Walker's 3rd and final flight. And last but not least, Payload Specialist 2, Rodolfo Nerivella of Mexico. Rodolfo Nerivella was born on February 19, 1952 in Chilpancingo, Guerrero in Mexico. He earned a bachelor's in mechanical and electrical engineering and a doctorate in electromagnetic radiation, specializing in waveguides. Along with Earth observation and some small experiments, Nerivella would also be observing the deployment of the Mexican satellite Morelos B. This is its only flight. On November 26, 1985, at 7:29 p.m. Eastern Time, with no postponements, scrubs, or delays, Atlantis lit up the Florida landscape and the shuttle program's second night launch. With this launch, Atlantis set a record that would not be beaten for the remainder of the program. Fastest turnaround from launch to launch. As you'll recall, we saw OV-104 just 2 missions ago on STS-51J, which was launched on October 3, 1985. So, Atlantis performed an entire mission, landed at Edwards, was ferried back to Kennedy, moved to the orbiter processor facility, had any necessary repairs or modifications made, rolled over to the VAB, was lowered onto the stack, rolled out to the pad, and launched again, all in 54 days. This is especially notable because if that pace was sustainable with a 4-orbiter fleet, NASA should be able to perform a launch every other week. The direct ascent proceeded smoothly with only 1 ohms burn required to circularize their 350-kilometer high orbit. First on the agenda, as always, was opening the payload bay doors, followed shortly by activating the Cephas and Deimos experiments. We of course know Cephas by this point, and we've actually seen Deimos before as well. On this flight, the experiment would be growing large crystals with greater size and purity than is possible on Earth. Next up, about 7 hours into the flight, was the first in what I've called in my notes the PAM-D Satellite Parade, which is a series of PAM-D comsats that will be punched out over the next few days. The first was Morelos B, which was the second in a series of satellites launched for Mexico. The satellite would be unremarkable except for A, the presence of Nerivella on the flight, and B, the fact that Mexico had suffered a devastating earthquake just 2 months earlier. The earthquake was so disruptive that Mexico decided that they had more pressing issues to deal with and that they wouldn't be able to use the additional capacity for about 2 years. So rather than being sent directly into its slot on the geostationary ring, Morelos B was placed into a geo-ish orbit, where it would take about 2 years to drift to its proper location. This change in orbit was actually the reason for STS-61B switching to be a night launch. On flight day 2, OSSAT-2 was deployed, joining its sibling satellite, which was deployed on STS-51I. And lastly, on flight day 3, RCA's SATCOM K2 was deployed. SATCOM K2 was notable because it utilized the new PAM-D2, which was a new, more powerful version of the PAM-D perigee kick stage that we're all so familiar with. What's interesting is that SATCOM K2 actually had less mass than Morelos B and OSSAT-2, so I'm guessing that the difference is that SATCOM was probably able to get a lot closer to its final orbit with the PAM-D2 and save fuel for station keeping and thus mission longevity. Day 3 was also a special one for the crew since it was Thanksgiving. While the crew wasn't exactly able to sit down to the big traditional dinner, they were able to celebrate with turkey and some pumpkin bread. Day 4 is where stuff really got interesting. With all of the payloads deployed, the extravehicular mobility units inspected, and the cabin pressure lowered to 10.2 psi to make things easier on the EVA crew, it was time for Jerry Ross and Woody Spring to head outside. Both men were equipped with additional instrumentation so that doctors on the ground could examine how the different construction techniques they would be testing impacted their body. Maybe the crew would discover that one technique was easier, but the doctors would discover that their oxygen usage was too high to be practical. Something like that. Much like Gemini 12, Ross and Spring would be doing work that on its own didn't really do very much, but close observation and evaluation of that work would provide the critical insight required to plan future missions. It was also an important test for the concept of practicing for an EVA in the neutral buoyancy pool. If the assigned tasks could be completed in a similar amount of time and with a similar level of difficulty as the pool, it would be further validation of this useful EVA training technique. In order to investigate techniques and capabilities related to in-space assembly of large structures, the EVA crew would be working with 2 construction kits with differing philosophies: experimental assembly of structures and extravehicular activity, and assembly concept for construction of erectable space structures. Ease and access. Ah, now the episode title makes sense. Let's start with access, since that's what the crew started with. Access consisted of 93 1-inch diameter struts, much to the delight of fans of Kerbal Space Program. The struts were split into 4.5-foot long longerons and 6-foot long diagonals. And since it's been a while since I've done metric conversions for our European friends, that's about 1.4 meters and 1.8 meters. Rather than bolting these struts to one another, they all just sort of snapped together, with little sleeves that slid over the connections to keep them secure. It sounds to me like a combination of the K'NEX building toy and a camping tent. The struts would be assembled into a triangular prism they called a bay. Imagine an equilateral triangle, now extrude it so it's 3D. That's the shape of the bay. Rather than just assemble these things freehand, Access included a foldable assembly jig. This was a structure in the shape of a bay that had places to stick all of the struts as a bay was being assembled, which was easier than dealing with all the elements floating individually. Once a bay was completed, the jig would move it up, clearing the assembly area for another bay. So one bay at a time, this truss-like structure would grow up and out of the payload bay. With all 10 bays in place, access rose 45 feet, or 13.7 meters. And I'm sure you're wondering, wait, what if they had an emergency and had to re-enter without much warning? Don't worry, the entire structure was easy to cut loose so that they could close the payload bay doors in a hurry and head home. For the first EVA, access was assembled and then disassembled, all in just under an hour. And since they were so far ahead of schedule, they did another full assembly and disassembly cycle. Next up was ease. Ease had a different philosophy than access. Rather than 93 small, lightweight struts, ease consisted of 6 pretty sizable beams, with each beam being 12 feet long and weighing 64 pounds, 3.6 meters and 29 kilograms. The beams still snapped together at their ends, forming a big tetrahedron, but with the additional element size and the lack of an assembly jig that could build the entire structure, it would be a different challenge. The first 3 were easy, just form the bottom point of the tetrahedron, attaching 3 struts together on a structure in the payload bay. But to connect the top 3, the EVA crew members had to climb up the beams and connect them while floating free, connected by tether, of course. Despite sounding somewhat daunting, the crew actually breezed through the task. They stationed 1 person at the bottom and 1 at the top, assembling and disassembling the tetrahedron 4 times. Then they switched places and did it another 4 times, with each iteration getting a little faster. It took about 10 minutes to assemble and about 7 to disassemble. With their construction work complete, the last task was for Woody to gently deploy a station-keeping target for use in the next experiment. I actually couldn't find a ton of information about the target itself, but after inspecting photos, I'd estimate it's about a foot or 2 in diameter. And if you imagine assembling 3 circular discs such that they're all intersecting and perpendicular to each other, you've got a pretty good idea of what it looks like. Once the EVA crew was back inside, the target was used as part of the Orbital Experiment Digital Autopilot, which was shortened to OXDAP, with the DAP being the flight control software for the orbiter. The pilot crew made small maneuvers around the target, station keeping with it, on both the current digital autopilot and the new one. The goal was to update the orbiter software to use less propellant while station keeping, but also to evaluate software that could be used on a potential orbital maneuvering vehicle. This is that space tug that I mentioned near the beginning of the episode. One thing I found interesting was that I can't find the mass of the station-keeping target in the official press kit, which typically lists the mass of all deployables. But no worries, that's why we consult multiple sources. I took the values from the press kit and added up the mass of all 3 ComSats, and then consulted Johnson Space Center's Space Shuttle Mission Summary Reference, which lists tons of stats about every flight in a concise format. Subtracting the Mission Summary Reference deployable number from the press kit number tells us that the station-keeping target weighed -9 pounds. Well, over 30 years, I guess sometimes stuff slips through the cracks. Flight Day 5 was spent on more experimenting with the new digital autopilot, tending to the mid-deck experiments, and letting the EVA crew rest. But on Flight Day 6, it was time to suit up again. The goal on this EVA was basically the same as the first, but with a couple of differences. Think of it sort of like an advanced version of EVA-1. They built the first 9 bays of access like normal, but for the 10th, Jerry Ross moved over to the manipulator foot restraint on the end of the shuttle's robot arm. Mission Specialist Mary Cleave then moved Ross up to the top of the 40-foot structure, where he assembled the last bay at the top. On the way down, he also ran a cable along the access structure. The idea here was to test the ability to assemble the structure in place without an assembly jig, as well as running cables and wires along an existing structure. With solar panels, experiments, and who knows what else, there would be a lot of exterior cables to manage on any operational space station. With Ross still on the end of the robot arm, Spring detached access from the payload bay, allowing Ross to just lift up the entire structure, twisting it around. This task, in addition to making Ross look ultra strong, was meant to evaluate how easy it was to carry and move large structures in space. After swinging the truss around for a while, Ross lowered it back down, Spring reattached it, the pair switched places, and Spring was moved partway up on axis. Once he arrived, he replaced a few struts, simulating in-place repair of a station structure. After that, he also got to try manipulating the entire detached truss. They then reattached and disassembled the structure, packing it away to take home. Next was another run at ease. First, they stuck 2 ease beams end to end, making a 24-foot-long linear structure, which emulated the heat pipes NASA thought might be used on the future space station. Spring basically just swung this around for a little bit to see how it went and how easily he could control it, and then the pair assembled the rest of the ease tetrahedron. With Spring still on the end of the RMS, Ross detached the tetrahedron, and Spring lifted up the 6-element structure. At 450 pounds, it was considerably more massive than the 190-pound Access, but Spring had no trouble keeping it under control. At the end of EVA-2, the only real issue popped up. Ease would not snap back into its support structure. But no matter, the crew simply took out a backup connector, snapped Ease into that, took the tetrahedron apart, and then brought the faulty connector inside with them so that they can inspect it later. The 2 EVAs, lasting 5 hours and 33 minutes and 6 hours and 41 minutes respectively, were completely successful. Ross and Spring were able to provide priceless data on how real-world space construction went. Their feedback included strong praise for the fidelity of the neutral buoyancy simulations and their EVA training in general, as well as concerns about hand fatigue in the pressurized gloves. Ultimately, space stations would not be built manually like this, or at least they haven't yet. The trouble is that stations don't just need structural members. You need to have lots of cables and pipes and conduits and whatever else. Assembling that all in space is more trouble than it's worth, so when the time came to build the ISS, its backbone truss was constructed on the ground in a few big segments that were then connected in space. Even without this technique catching on, I think this was an important flight for EVA. We've seen some ambitious spacewalks in the shuttle program so far, but the amount of choreography and attention to detail on this one was pretty intense. All of those little access pieces were free-floating, and there were no safety tethers on them or anything like that. So it took a lot of care and conscious effort to perform complex tasks while making sure that all of the tools and equipment were properly secured. I think it's safe to say that this flight expanded the envelope for EVA capability and probably helped pave the way for some of the incredibly difficult satellite servicing missions to come. Since the upcoming weather looked a little iffy, Mission Control decided to bring Atlantis home 1 revolution early. And since the weather had been a little iffy earlier, Commander Shaw set the spacecraft down on the concrete runway at Edwards, avoiding the mud plains of the desert left soggy by a little bit of rain. After a flight lasting 6 days, 21 hours, 4 minutes, and 49 seconds, Atlantis had completed its second mission. And with that landing, we close out a remarkable year for human spaceflight. Over the course of 307 days, NASA had launched 3 orbiters on 9 missions, spending 55 days in orbit. And yes, it was 3 orbiters, not 4, since Columbia was being upgraded, so it missed the boat. We saw classified missions, creative on-the-fly solutions, difficult rendezvous, boatloads of science, satellite wrestling, and, if memory serves, approximately 400,000 commercial comsats deployed. Or at least it felt like it. 1985 was a year to be proud of, and a year to remember. Next time. Speaking of Columbia, after a year and a half of upgrades, OV-102 was back on the launch pad with STS-61C. We've got a ComSat, some getaway specials, a snazzy new tail camera, and a grapefruit-based prank to get into. Ad Astra. Catch you on the next pass.